Hello everyone, welcome to the ninth topic of the SS2 first term physics curriculum. Now the topic we are looking at here is machines, and it's a pretty broad topic which is why it's divided into two. So in this video we'll be doing the part 1 which covers what we know as mechanical energy. We should be able to define or explain mechanical energy and also state the conservation of mechanical energy. Explain the concept of the conservation of mechanical energy. Then we should from what we've learned from mechanical energy, be able to now define what machines is. Now, many people often define machine as any unit or system that makes work easier. But from the perspective of physics, from the perspective of mechanical energy and the conservation of mechanical energy, what is a machine is what we'll be looking at this point. So we define it from those perspectives. After that, we now look at some 3 important factors to consider when dealing with machines. One of them being mechanical advantage of a machine, the second being the velocity ratio of a machine, and then the third being the efficiency of a machine. And then after that, we then solve some problems regarding mechanical advantage, velocity ratio, and efficiency of machine. So that will be what we'll be covering in this part of machines. And please, if you're yet to be subscribed to the channel, kindly take a moment, click the subscribe button, and also click the notification bell icon so that you get alerted every time we put out a new content. That way you will not miss the remaining videos that is to come your way. And also help us to reach many more students like you who need helpful videos that we are making right here on our channel by sharing the videos. And also encourage them to interact with the video by dropping a like and a comment. Please, if you have any question, anything you would like us to do at all, feel free to put them in the comment section and we will always attend to all of your comments. Thank you so much for that. Please don't forget to share the videos. Now let's dive into machines by looking at what we have itemized in this topic. To start with our study of machines, we have to review a few things, starting with what energy is. Now you recall that we said energy itself is the ability to do work. This is let me use the word capacity now. Capacity to do work. Okay? And we said work is done when a force moves its point of application by a certain distance. Okay? Work is done when a force moves its point of application a certain distance. Okay, now you see these two things help us to understand machines better. So you see, machines have the capacity to do work in the sense that they can apply force to an object and cause it to change position. Okay, so when we talk about machines, we have to study the energy that such machines have. And the type of energy you find in machines is what is known as mechanical energy. So let's define what mechanical energy is. Mechanical energy is the energy possessed by an object due to its state / position. Now in this case, this is known as potential, or its motion. So this is why we say there are 2 types of mechanical energy. We have potential energy and kinetic energy. Now, to define potential energy, that will be the energy possessed by a body due to its position or state or configuration. Then kinetic energy will be the energy possessed by a body due to its motion. Now, you see, in our study of mechanical energy, when we want to find potential energy of a body, we denote that PE. PE of, say, an elastic object. Elastic object, for example, is often given as half kx squared, where k itself is the elastic constant, and then x is displacement. Okay, and the same potential energy now for objects held above ground. This is given as mgh, where m is mass, g is gravitational acceleration, and h is height above ground. Now, that's the case for potential energy. Don't forget that it's the energy possessed by a body due to its position, state, or configuration. Now, for kinetic energy, which is the energy possessed by a body due to its motion, we denote that Ke, kinetic energy. It is given as half mv squared, where m is mass and v is velocity. Now, you see, because it is in motion, it has a change in displacement with respect to time known as velocity. So these parameters we've looked at, or phenomena we've looked at, are very important to the understanding of machines, because there's no how you discuss machines without talking about the energy that the machine has, that is the machine's capacity to do work. And there's no how you talk about it without looking at objects that are taken from one height to another, or without looking at objects taken from one point to another with a certain speed. So hence, you must understand potential energy and kinetic energy. And there are some machines that are made of springs, which means you need a spring constant and be able to calculate the potential energy or the work done by such spring by using the equation half kx squared. So this is why we have to look at this. Now, let's apply to some questions before we then go to define what a machine is. This question says, calculate the work done by a machine to carry a load of mass 800 kilograms through a vertical distance of 5 meters. We are told to take gravitational acceleration as 10 meters per second squared. So basically, this machine picks up the object and lifts it 5 meters high. And we see that the mass is 800 kilograms, which will mean the weight is 8,000 Newton. But this is how you solve the work done. The work done in this case is the same thing as potential energy. So here's the solution. Work done equals mgh. Now, the mass is 800 kilograms. So we multiply that by g, which is 10 meters per second squared, and then multiply that by the vertical height it goes, which is 5 meters. Now, when we multiply all of this, what do we have? This is 800 times 10, that becomes 8,000. Now, 8,000 times 5. You can just say 8 times 5 will give you 40. Then we have 1,000, so 40,000 joules being the unit of work done, and the same thing as the unit for energy. You can just write this as 40 kilojoules. And that's the solution to this problem. This question says, a catapult is used to project a stone of mass 50 grams. Now, if the rubber of the catapult has an elastic, this should be AN. So an elastic constant of 200 Newton per meter, and was stretched 5 centimeters. What speed can it give the stone? So you see here that the elastic catapult has a potential energy that can be translated into kinetic energy in the stone. So for questions like this, you have to assume that no energy is lost. So this is how you solve a question like this. Assuming no energy is lost, then potential energy equals kinetic energy. And what is the potential energy of an elastic material? That is half kx squared. Okay, so we equate this to half mv squared, where v here becomes speed. So it's easy to see that half cancels half. So we have kx squared equals mv squared. Now k is given as 200 Newton per meter. So we put that here, 200 multiplied by x. X is the displacement, that is the stretching of the elastic rubber. And we see here that it is stretched by 5 centimeters. Bringing that to meter, we will have 5 over 100. Now in bracket squared. Equate this to the other side here where we have the mass of the stone, 50 grams. That will be 50 over 1000 multiplied by v squared. So let's solve this. If we're going to tidy this up, we'll now have 200 multiplied by 25 over 100 times 100. That will give you 10,000. Okay, and we equate this to 5 over 100 V. So from here we can see 0 cancels 0, 0 cancels 0, 25 here 1, 25 here 4. Right? So we have 2 over 4. So 2 here 1, 2 here 2. So we have 1 over 2 equals 5 over 100 V. So making V the subject here, we then say V equals 100 goes here to be 100 over, because 100 times 1 is 100, then 5 comes here, 2 times 5, that is 10. Remember, it's V squared. V squared because of this. So once we put the square back, now we have 100 over 10. What we have here is V squared equals 10. So the value of V itself will now be the square root of 10, which should be approximately 3.16. And speed is measured in meter per second. Now, the concept behind this type of solution is what is known as the conservation of mechanical energy. So let us now look at what the conservation of mechanical energy states and how we have applied it to this question. So like I said, the question we just solved dealt with a machine, being the catapult here, converting the potential energy in a stone, in the rubber rather, the potential energy in the rubber, the elastic part of the catapult, into kinetic energy in the stone. Okay, so that kind of a case, we had to assume that the energy is conserved. That's why we say assuming there is no energy lost, and then we equated the potential mechanical energy into kinetic mechanical energy. Now, that statement there, assuming no energy is lost, comes from what we know as the conservation of mechanical energy. And what that states is that when you have a closed or isolated system, now what that means is that a system where energy is not shared with the surrounding, okay, in such a system like that, the total mechanical energy is conserved. Now, in general, there's another one we call the conservation of energy alone. That one doesn't focus on mechanical energy. That one is telling you that in a closed or isolated system, energy may change from one form to another, but the total energy is conserved. Like for example, if you have electrical energy in a system, it may be changed to kinetic energy and heat energy. Now the products there being the kinetic energy and the heat energy, if you add them up, it will be the same thing as the electrical energy that is supplied into the system. That is because none of those energy is lost to the surrounding. Okay, but here, because we are dealing with machine, we are limiting it to just mechanical energy. So conservation of mechanical energy follows the same principle of the conservation of energy. That is, in a closed or isolated system, the total mechanical energy in that system is conserved. That is, even though energy may change form within the system, the total energy remains the same. Let's put that down. The principle of conservation of mechanical energy states that in a closed or isolated system, the total mechanical energy is conserved, or we just say constant, though energy may change form. Now, another way to state this is from what we learned from the conservation of energy at large. That is, energy is neither created nor destroyed, but may change from one form into another. So since you are dealing with machines here, you may see some systems where potential energy is translated into kinetic energy, and vice versa. That is, kinetic energy can also be converted into the potential energy. And there are some systems also where you see that a different form of energy comes in and then it is converted into mechanical energy. And that mechanical energy can be either kinetic or potential. So all of this follows the principle of conservation of energy. Let's not forget what it states, that in a closed or isolated system, the total mechanical energy is conserved, though energy may change from one form to another. And that's the principle of conservation of energy. What is a machine? This question is one that always brings a smile to my face whenever I'm faced with it. Majorly because it reminds me of a scene in one of my favorite movies of all time. Now, in that movie, a professor asked in his class, "What is a machine?" It is so iconic because of what transpired after that question. Now, the protagonist in the story responded to that question by saying, "A machine is anything that reduces human effort." Now, that response is correct, but the professor went on to say, "Can you please elaborate?" And then he thought of it and said, "Okay, anything at all that you apply to make work easier or faster is a machine." And then he gave examples such as whenever you are in a room that is hot and then by the click of a remote you turn on a fan, that remote is a machine. Whenever you need to talk to a friend who is very far away from you, you pick up the telephone and then you make that call. In that case, the telephone is a machine. Said, in fact, we are surrounded by machines. Everything we do, the nib of a pen, even the zip on our pants. The professor looked at him and said, "What kind of definition is that? Is that what you will put in an exam paper?" And then gave the chance to another person to define what a machine is. And then this person went on to say, a machine is a system that consists of body parts that is so connected that when you apply force, it is able to do work. And then he gave this long, bookish kind of definition, and the professor loved it because it seemed more eloquent in the way that he defined machine. Now, here's what I learned from that scene in the movie. Both of them actually defined machines, right? But most of the times we are expected to define it in a particular way, probably for exams to score more grades and things like that. But it doesn't matter how you define machines or in how many words you define machines. There are just some things that is expected of you in your definition of machine. So when you define machine, whether you define it as the protagonist of the movie I just described to you, or you define it as the other person who gave a bookish definition that is such a mouthful, it doesn't really matter. What everyone should look out for is, does it contain the main things that helps us to understand what a machine is. So when you come out and say a machine is something that makes work faster, even though it is true, there are still some elements that are missing in that definition. And if you give the definition that the other person gave as something that has body parts so connected in such a way that you apply force, and it's a mouthful, I tell you. But if you still miss out some important part of that definition, you would have missed it. So what is it that is expected of you when you define a machine? You see, for something to be qualified to be called a machine, it means that it allows you to apply force at a point. Now, that force that you apply at that point is called effort. And then it transmits the force you apply to another point in order to overcome a resisting force. Now, that resisting force is called a load. Now, the way it does it is in such a way that it is both either convenient and also effective. That it can be convenient and effective in transmitting that your effort to overcome the resisting force known as load. And once you have those elements in your definition, you have described what a machine is. So let's put that down so we do not forget what to mention when you are defining machines in physics. A machine is any device which allows you to apply force at a point and it transmits the force to another point to overcome a resisting force. That is load, in a way that is convenient and effective. So what are the things we see here? You apply effort, apply force. Now, apply force means you apply an effort, then it transmits your effort to overcome resisting force known as load in a way that is convenient and effective. These are the elements that must make up your definition of a machine for it to describe a machine without error in physics. So when you're asked to define a machine, don't forget these things. It is something that allows you to apply effort, then it transmits the effort to overcome a resisting force known as load in a way that is convenient and effective. And that is how you can define a machine. Some of the things you have to consider when working with a machine is, in the first case, mechanical advantage, or as it is often called also, the force ratio of a machine. You see, the reason why you use a machine is because it allows you to apply force in a way that is convenient and effective. That is, you should be able to do the work in a way that is easier than you would normally do it. Now, a machine should not make life difficult for you. It should make it convenient. It should make it effective. Okay, so what do we mean by the mechanical advantage of a machine? See, in a simpler term, mechanical advantage of a machine refers to the ability of a machine to overcome a large load by the application of a small effort. So when you want to calculate this, it is done as the ratio of load to effort, or what we call the work output over work input. Let's put all of this down. The mechanical advantage of a machine refers to its ability to overcome a large load by the application of a small effort. Now, when we do this mathematically, we say mechanical advantage denoted MA equals work output over work input, or we say mechanical advantage equals load over effort. So because both of them are in Newton, that's why it's called force ratio. And as you can see, Newton cancels Newton, so mechanical advantage does not have any units. So it does not have units. Now, one thing you should know is that when MA is greater than 1, then that machine is able to overcome a large load with a small effort. You shouldn't be having a machine with mechanical advantage equal or less than 1, because if it is equal to 1, the same effort you would have applied normally is what you are applying through the machine as well. And when it is less than 1, it means you are applying even more effort to overcome a small load, and as such, that device is not qualified as a machine. What is a machine? Should make work easier. That is, you apply a little effort to overcome a large load. So mechanical advantage should be greater than 1 for good machines. So this is what we mean by mechanical advantage. Now let's look at velocity ratio. Now that we can define what mechanical advantage is, let us now look at another important phenomenon that has to be understood when working with machines. Now, this is known as velocity ratio. Okay, now in physics, velocity ratio of a machine is defined as the ratio of the distance moved by effort to the distance moved by the load. Now, you see, when you're using a machine, there's an amount of distance that your effort goes to. And you know, when you have force times distance is basically what you know as moment, right? So when you multiply that, when you look at the distance moved by the effort that you are applying to a machine, and then you look at the distance that the load travels with respect to that and take it as a ratio, what you are considering there is the velocity ratio of a machine. Let's put it down. Velocity ratio is the ratio of distance moved by effort to distance moved by load. Now, that is, if we're going to write it down, we say VR, where V stands for velocity, R stands for ratio, equals distance moved by effort all divided by distance moved by load. Now you see, different machines have different ways by which you can determine their velocity ratio. Now what it depends on is the shape in which the parts of the machine is made of. So a good understanding of geometry will help you solve problems on velocity ratio as regards a machine. For example, some machine parts that are circular in nature will require you to understand that the circumference around a circle is 2 pi r. Whereas for some machines that take objects through vertical distances, you would also need to understand how to get the distance moved by that effort and the distance moved by load along that vertical path. And there are some machines that involve screws and things like that you also have to understand how to find the path through which effort moves and the path through which the load moves. And a good understanding of such kind of geometry will help you solve velocity ratio without a problem. Now, before we go on to efficiency, it is important that I make mention of this. Although there isn't anything like an ideal machine, every machine has a little bit of limitation because it's either it is working against friction or it's working against other type of resistive kind of force, right, which limits the efficiency of such machine. But if there were ever any such thing as an ideal machine, in such a machine, the velocity ratio and the mechanical advantage will be the same. So in most cases, you find that in fact in all cases, I think I can say in all cases, because there is no such thing as an ideal machine. I see air quotes around ideal machine there, because we do talk of ideal machines even though there isn't any one of that. I don't know, maybe you might be able to produce an ideal machine. I think it's one of those things that we consider impossible, right? But we still leave room for the possibility of it. So if there is ever anything called an ideal machine, right, in that type of machine, the velocity ratio and mechanical advantage will be the same. But in other machines that we know, velocity ratio is always greater than the mechanical advantage. Now the difference between this velocity ratio and the mechanical advantage accounts for the efficiency of the machine. So when we talk of efficiency, you see where that plays out. But let's note that for an ideal machine, mechanical advantage and velocity ratio is the same, because this is something you will use in some kind of calculations, because there are some kind of calculations you'll find in your exams that you'll be taking where they tell you to assume you are dealing with an ideal machine, and an ideal machine will be 100% efficient. Okay, so that is why we say in such kind of machine, velocity ratio and mechanical advantage are the same. So let's note it. In an ideal machine, mechanical advantage equals velocity ratio. So once again, a quick recap. Velocity ratio is defined as the ratio of distance moved by effort to the distance moved by load in a machine. Thank you. So away from machines that do not have 100% efficiency. Remember I mentioned that for an ideal machine, that the efficiency is 100% because velocity ratio and mechanical advantage are therefore the same, right? So since there isn't such, because they always have to work against friction, the moving parts in the machine have friction to battle with, to contend with, right? And though those machines usually come with other things that can help them limit friction, but it doesn't get it to the 100% mark. I mean, no matter the amount of lubricants you use to reduce friction, amongst using the ball bearings, streamlining the machines, amongst other kind of precautions you can take against friction, it doesn't quite get it to 100% efficiency. But no matter what kind of machine you have, you can still get the efficiency based on the following parameters. So to calculate the efficiency of a machine, it is given as efficiency equals useful work done by machine to work done by effort. Okay, and then when you multiply this by 100%, you get your efficiency in percentages. So another way to put this is to say efficiency equals work output divided by work input or multiplied by 100%. So calculating efficiency is done in percentage. Don't forget, you can't get 100% machine. That is what we call an ideal machine. It's non-existent because of friction amongst other factors that machine always work against. Okay, so outside of this, there's another way you can get efficiency using mechanical advantage and velocity ratio. And that comes from when I mentioned that for an ideal system, an ideal machine, velocity ratio equals mechanical advantage. So that means to get efficiency, it should be a ratio of mechanical advantage to velocity ratio. So that is, efficiency is also mechanical advantage divided by velocity ratio. Then when you multiply this by 100%, you can put your efficiency in percentage form, just like we did in this case, and this case. Now, all three of these equations are telling you the same thing. Okay, but depending on the kind of question you're trying to solve, that's when you choose which of the equations will work for you. Okay, there will be some cases where you'll be given the useful work done and the work done by effort, and then you can put that into this equation and solve. Sometimes they will give you the mass of the load or the weight of the load itself, and then they tell you the effort applied and the distance moved by effort amongst other things. Then using that, you can calculate your work output, work input, and use this equation. And then there are some times where you'll be given mechanical advantage and velocity ratio, and then you use this. Then sometimes again, you could be given the load, given the effort, distance moved by load, distance moved by effort. Don't forget that you already have equations for mechanical advantage and velocity ratio. Let me remind you again. Mechanical advantage itself is load over effort. And velocity ratio is what? Distance moved by effort divided by distance moved by load. So you see, you can combine these two also to make up this equation and then use them to solve the efficiency. Now, one thing that that examiners find to do, that they do commonly rather, when they set questions like this, is sometimes they give you the efficiency itself and then ask you to find the value of the load or the effort applied given other parameters. So you should know how to change your subject or formula depending on how the question comes. Now, to help you with questions like this, we're going to solve a few type of such questions, and I'll be showing you some tips that you should keep to mind whenever you are solving questions on machine, so that you can always get it right every time you solve it. So if you're ready, let's solve some examples. This question says, a machine whose efficiency is 80% is used to lift a load of 8,000 newtons. If the velocity ratio is 5, calculate the effort applied. So in this case, we have to find the effort applied to lift this load of 8,000 newton. And since the efficiency is 80%, we know that the effort applied to lift this load is going to be significantly lower than 8,000. So let's find the actual value of the effort required to lift this 8,000 newton using this machine. And please pay attention so you see the steps involved to solve questions like this. Now, you see that in this case, we have velocity ratio and efficiency. So we can begin by using the equation for efficiency that involves mechanical advantage and velocity ratio. So we say efficiency equals mechanical advantage over velocity ratio. Okay? So from here, efficiency is 80%, that is 80 over 100. 80 out of 100 equals the mechanical advantage, which is unknown, divided by velocity ratio, which is 5. Now, when you make velocity ratio the mechanical advantage subject of equation here, you see that the mechanical advantage therefore becomes 5 times 80 divided by 100. And when you break this down, your answer is going to be 4. So the mechanical advantage is 4. Now, let's find the effort applied. Don't forget that mechanical advantage itself is load over effort. So what this implies is that the effort is going to be load divided by mechanical advantage. So you see how we find effort from efficiency now. Okay, so from here we just go straight and say efficiency equals the load carried here is 8,000 newtons. 8,000 newtons. Now we divide that by the mechanical advantage, which is 4. Now 8,000 divided by 4 is going to give you 2,000 newtons. That is, you only require 2,000 newtons of force to raise 8,000 newton of load using this particular machine. And that's the solution to this question. This question says, a machine of velocity ratio 6 requires an effort of 400 newtons to raise a load of 800 newtons through 1 meter. Find the efficiency of the machine. Now, to solve questions like this, by the way, it's from the UTME of 2010. One thing that is certain is it depends on how good you are with numbers. If you're the kind of person who is very good with numbers, then you can put all the equations together and then solve in one single swoop. However, if you're not very good with numbers, you can break it down and solve it in steps. Okay, so I'll show you how to solve it in steps so that you don't make errors. One thing is certain, when you break questions like this down, the chances of you getting the answer correctly is always very high. But when you put everything together into one equation and you solve it in one single swoop, the thing is, there are tendencies that you might make error while solving, and you won't even be able to catch it when you make such an error. So it makes it possible that you miss the answer while using that type of method. And here's the thing about it. Some think the more the steps you use, the more your chance of scoring a high grade in an exam, but that is completely false. You see, it all depends on your instructor. If your tutor is telling you, I would like you to solve questions like this in this particular way, it's often good to solve it the way that they have told you to do it, even though there are other ways, except if you challenge it in class and say, but what about this method? It's also correct. If the instructor then goes on to say, no problem, it's also good, then you're good to go. Now, that does not mean that your methods or other methods are wrong. It's just that some people prefer that you do things the way they have given it to you. Now, that's not science as far as I'm concerned. That's basically you are cramming or using memory method to learn. So I would prefer that you learn the right thing. But for those who wants to study to pass exams, sometimes you just have to allow some things just so that you get your goal, since that's the goal for such kind of people. But here we are showing you everything the way it should be, and then you can apply the method based on what you have learned. That's how we do it right here on Oya Learn. So let's solve the problem. What do we have in this question? We see we have velocity ratio, which is 6. We see that the load is 800 newtons and effort applied is 400 newtons. And then we are asked to find efficiency. Now, please note, efficiency is always, you can put efficiency either as a ratio, or you put it as decimal fraction, or you put it as percentage. Now, most times we often give efficiency in percentage, okay? So let's solve it using that method. Now, we know efficiency should be mechanical advantage over velocity ratio times 100% if we are leaving it in percentage. Now, when I said you can put everything into one equation and do it in one single swoop, that will mean that you account for the fact that mechanical advantage itself is load over effort and plug that into this equation and then say all divided by velocity ratio. But if you want to solve it in step and avoid error, just go straight to say mechanical advantage equals load over effort, which is 800 newtons divided by 400 newtons, which would give you 2 as your mechanical advantage. You can then go on to say efficiency equals 2 over velocity ratio 6 multiplied by 100%. Now, when you break this down, this is 2 year 1, 2 year 3. We see that efficiency therefore becomes 1 over 3 multiplied by 100%. And this is going to give you 33.33%. Now, the reason why it's safer to solve using this method is that now for some students, when they try to put everything together, now observe this method. When you say efficiency equals mechanical advantage, which is load over effort, now all divided by velocity ratio, which is, let me just put it as the symbols now and say multiplied by 100%. Now, some are unclear as to how they are supposed to solve problems like this, and while doing that, you might end up making some errors. Some will think that there are cases where the denominator moves up, but not in this case, because you see that the large divisor is here. Okay, instead it is efficiency that comes down. This is not the same thing as, look at this now, A over B all over C is not the same thing as A all over B divided by C. They are not the same thing. And in this case now, this is basically AC over B, but this is A over BC. And some students don't understand how to deal with fractions like this, or have not solved problems involving fractions like this. Okay, so for those kind of students, it's safer that you go through this route and solve each of them bit by bit before you combine it into the main equation like we did here. However, if you are good with numbers, you can go on with this and solve it without problem, and you will still end up with 33.33%. I hope you've learned something. This question from the 2024 UTME says, an effort of 40 newtons is applied to a machine to lift a mass of 60 kilograms. Now, determine the mechanical advantage of the machine, taking gravitational acceleration to be 10 meters per second squared. Now, to solve question like this, what you do? You see, we are asked to find mechanical advantage. And mechanical advantage equals load over effort. We have effort given in the question, but how do you find load? Load is basically the weight of what you are lifting, which is mass times acceleration due to gravity. So mechanical advantage becomes mass 60 kilograms multiplied by acceleration due to gravity 10 meters per second squared, all divided by the effort applied, which is 40 newtons. Now this would give you 600 newtons divided by 40 newtons. So you see newtons cancel newtons because mechanical advantage does not have any units. So mechanical advantage here therefore becomes 0 cancel 0, 4 in 60. 4 will go in 6 once, remember 2 in 25. So you see here that the mechanical advantage of this machine is 15. And that's the solution to this problem. Here is a longer question. We have a block and tackle system. Now, a block and tackle system is a system of pulleys. It has more than one pulley. So you have 2 pulleys, 3 pulleys, 4 pulleys. They are called block and tackle system. So it says a block and tackle system of velocity ratio 4 is used to raise a load of 500 newtons. Now let me just pause here. You see, when it comes to types of machines, I mentioned earlier that velocity ratios, the way we calculate for it is different for different types of machines, right? And it's often dependent on the geometry, that is the shapes of the machine. Okay, so when we get to part 2 of machines and begin to look at different types of machine, I will elaborate more on that, showing you how you can develop an equation for velocity ratio for different types of machine. Like in the case of block and tackle system, let's just say spoiler alert anyways, for block and tackle systems, the number of pulleys involved is often the velocity ratio. Let's take that as a spoiler anyways. But moving on with this work here, we have been given the velocity ratio here to be 4. But for different types of questions you might find on machines like this that has to do with efficiency and other things like this, the type of machine you're working with, the shapes of the parts of the machine determines the velocity ratio. So when we get there, I will elaborate more on that and then you get a fuller understanding. But let's continue with this question and see how we'll solve it. So we are told the velocity ratio is 4 and is used to raise a load of 500 newtons through a height of 20 meters. Now, if the total work done against friction in the pulley is 800 joules, we have to calculate first the total work done by the effort. The second part is to find the efficiency of the system and then finally calculate the effort applied. Now, please don't get this wrong. Effort applied is different from work done by effort. You see, the effort you're applying may be very small, but with the help of the machine, due to its mechanical advantage, it amplifies that your effort to give you a high amount of work done, and it's dependent on the mechanical advantage of that machine. Okay, so that's why I see in machines like this, you apply very little effort, but the work done by that effort is going to be very great. Okay, especially when the mechanical advantage is also high. Remember, I mentioned earlier that machines that have good mechanical advantage are always greater than 1. The mechanical advantage is greater than 1. Okay, so let's solve this problem and then we'll learn one or two as we go. Solution. Let's start with the first part, A. So we have to find the work done by effort. Now, what is the work done by effort? Remember that the effort is going to lift the load by the distance it has been asked to lift it. And then secondly, it's also going to work against friction. So that is, the work done against friction by the pulley will be added to the work done by effort. Okay? So that is, the work done by effort will then be, normally work done is force times distance, right? So the load itself has been given as 500 newtons. So work done by effort becomes 500 newtons multiplied by the distance traveled. Work done is force times distance. So the distance here is the height, which is 20 meters. Newton meter gives you joules. Plus the work done against friction, which is 800 joules. Now this would give you 500 times 20, that is 10,000 joules plus 800 joules. When you add this becomes 10,800 joules. Okay, so that's for the A part. We have the total work done by effort. Now let's go to the B part where we have to find the efficiency of the system. The B part, for efficiency of the system, you see total work output over work input times 100. That's the equation we are going to use in this part. Remember, I gave you about 3 to 4 equations that work for efficiency when we're talking about efficiency of a machine. This is the kind of question that requires you to use a different approach instead of the mechanical advantage and velocity ratio approach that we are used to. So here we see that efficiency is work output over work input. So we want to leave it in percentage, so we would say times 100%. So let's see what this would give us. From there we can now say efficiency is, the work output will be 500 times 20, because that's what is done by the machine. It lifts the load of 500 newtons through a distance of 20 meters. That's the work done by the machine. Now the work put into the machine is what we have calculated here, which is 10,800. All of this times 100%. So if you need efficiency as just a fraction, it would be this part alone. But leaving it in percentage is why we are multiplying by 100 here. So we see that this will give you 10,000 divided by 10,800 times 100%. Now this will give you 0.926 times 100%, and then our answer is 92.6%. That's for the efficiency of the machine. Okay, so now that we have the efficiency, we can now go on to find the final part, which is the effort applied. So let's see how we get effort. To get effort, we need mechanical advantage. And remember that efficiency itself equals mechanical advantage over velocity ratio. Okay? So that is mechanical advantage therefore becomes velocity ratio times efficiency. Now, what's the velocity ratio? Velocity ratio is what? 4. So we multiply that by the efficiency, which is just this fraction part. Okay? So now we have 10,000 over 10,800. So let's break it down. 0 cancels 0, 0 cancels 0. Okay? And when we consider here, 2 goes here twice. 2 goes here how many times? This will be 54. Okay? 2 still goes. 2 here 1, 2 here 2. Here that's 7, 27. So mechanical advantage equals 100 over 27. Okay? And mechanical advantage is supposed to be load over effort. So to get effort becomes, remember, mechanical advantage is load over effort. So effort becomes load over mechanical advantage. So what does that mean? The load is 500. Okay? So divided by mechanical advantage, which is 100 over 27. This would give you 27 times 500 over 100. So this here 1, here 5. So we have 27 times 5 as effort. And what's 27 times 5? 5 times 7 is 35. So 5, carry the 3. 5 times 2 is 10, plus 3, that's 13. So 135 newtons is the effort. So you see that in this machine, you are only applying 135 newtons. But because of the mechanical advantage of the machine, it amplifies this effort such that it is able to do a work of 10,800 joules. And then this is used to then lift the load by doing a work of 10,000 joules. That's the full interpretation of what we have here. So in case you have a question like this, by following these simple steps, you can also solve the question. But the answer to this one, for A part is 10,800 joules, the B part is 92.6%, and then the C part gives us 135 newtons. Now you try solving this question. It says, what effort will a machine of efficiency 90% apply to a load of 180 newtons if its effort arm is twice as long as its load arm? This question is from the 2018 UTME. Now, apply the methods that you have learned in this video so far to solve this question. Now, you can then compare your answer to what's gotten at the end of this video. So just take a pause on the video, try it out yourself, and then compare results at the end. Alright, now that you solved it, let's look at what we get here and then see if you got the answer correctly. Now, in this question, we see that efficiency is 90%. That's 90 over 100. That will give you 0.9. Okay, we have the load is 180 newtons. And then we are asked to find effort. But velocity ratio is given. Remember, velocity ratio is supposed to be distance moved by effort over distance moved by load. And since the effort arm is twice as long as the load arm, velocity ratio therefore becomes 2. Okay? So now using this, let's find mechanical advantage. That would mean efficiency 0.9 equals mechanical advantage divided by 2, which is velocity ratio. Now from here, we can now see that mechanical advantage becomes 0.9 multiplied by 2, which will give you 1.8. Now that we have mechanical advantage, let's find the effort. So 1.8, which is mechanical advantage, becomes load, which is 180 newtons divided by effort. Now what this implies is that effort is 180 newtons divided by 1.8. So effort is therefore 100 100 newtons. So the effort required here is 100 newtons. Now check it with what you have gotten when you solved it. And if you got the same thing as 100 newtons, put it in the comment section saying, I got it. Thank you so much. So now, folks, we've been able to look at what machines are. We've looked at it from the eyes of physics by first checking out what we know as energy, work. Then we looked at mechanical energy. We looked at the potential energy, kinetic energy. We're also able to state the conservation of mechanical energy and apply it to some questions. And now we've looked at what machines is. We've looked at velocity ratio, mechanical advantage, and efficiency. That about covers what we plan to cover for the part 1 of this topic. There's still more to look at when it comes to machines, such as the different types of machines and how you solve for efficiency in those types of machine. Trust me, it's an exciting one that you do not want to miss. So please, if you are not subscribed to the channel, kindly do so. Just take a moment, click the subscribe button. And so that you don't miss the next video, which would be on how to solve problems on different types of machines, ensure that before you leave the page that you click the notification bell icon so that once that video is posted, you will be notified. Thank you so much for being part of it so far. We have so much more coming your way, so stay tuned with us. Keep it locked with Oya Learn, a wonderful channel where we make your academic journey even way simpler. Thank you so much. I'll be seeing you in the next video. Bye for now.